Well, welcome to Spaceport America. I'm standing here in front of the Gateway to Space building, and this is the building that Virgin Galactic uses for their operation to carry passengers to space. We're standing on the taxiway that connects with the runway, so during mission days, the aircraft carrying the spaceship taxis out right where we're standing now, goes out to the runway and then takes off and goes up to about 50,000 feet and then drops off the spaceship, which flies on its own into space. So this building is also sometimes called the terminal and hangar facility. So at an airport, the terminal is the building where the passengers go to check in for their flights, to drop off their baggage and all those kinds of things. But the hangar, of course, is where aircraft are put inside if they need service or just to keep them out of the weather. So this building actually has both of those functions in it. The terminal part is the part here in the front with all the glass, and that's where the Virgin astronauts come for some final training and to prepare for their flights. And then behind that is the hangar where the spaceship and the carrier aircraft called the White Knight are used, or where they're parked when they require maintenance or just to keep them out of the weather. We've been using this building now for a number of years, and it's a really very large building. It has about the same amount of floor space as a large department store, and it's on 3 levels. And again, the hangar is the largest part of the building, but in front of me, right behind me, you'll see the 3 levels that have the areas that are used for conducting the missions. But we have a number of other customers here as well who carry only scientific experiments at the present time. Our oldest customer is a company called Aerospace. They're from the Denver area, and they've flown 14 times here from Spaceport America, carrying many, many different kinds of scientific experiments up to space. These are suborbital missions, meaning that the rocket goes up and then comes right back down under the influence of gravity just 15 or 20 minutes later. We're not launching to orbit here, but we do carry lots and lots of experiments. We have another customer that's flown many, many times called Aerospace. But we also have a number of smaller customers as well, and many universities come here to launch their rockets. Every June, we normally have an event called the Spaceport America Cup, where we bring thousands of people from around the world, something like 120 to 150 teams of college students to come launch their rockets, and have a couple thousand of their students come to launch those rockets in a competition to see who can come the closest to meeting the predictions of their flight. So we're standing here on the runway at Spaceport America. This is the runway where Virgin Galactic flies people to space from, and we use it for general aviation as well. Behind me in that direction are the buildings, the Gateway to Space building and the SOC building, the Spaceport Operations Center. And off in that direction, about 5 miles away, is what we call our vertical launch area. That's where we launch rockets that go straight up into space. So we've been launching from down there since 2006, and we've been operating from this runway going to space since last year about this time. So the runway that we're standing on is 12,000 feet long. That's about 2¼ miles long, and it consists of 14 inches of concrete on top of 4 inches of asphalt on top of another 20 inches or so of prepared soil that's been compacted and had some concrete mixed with it, so it's very hard and resistant to impacts when aircraft land. The runway, the numbers that you may see behind me, says 34. That means the compass orientation of this runway is 340 degrees. So it's pointed just a little bit off north, and this is the direction that most of the times airplanes are taking off, because most of the time the wind is from my back, and aircraft, whenever possible, take off into the wind. Again, this was built in 2010, 2011, and it was added to in 2012 and 2013. It was originally 10,000 feet long. It's now 12,000 feet long. So this runway has seen lots of operations. It's been used for many years now for small airplanes, and in the last 1.5 years or so, it's been used by Virgin Galactic for flying their White Knight 2 and their Spaceship 2, which is the space vehicle that they use to carry people to space. Also, over the last 3 years, we've used it to inflate very large balloons that Boeing has used for the purpose of carrying their space capsule up to 40,000 feet so that they can test the parachute system. We have this very nice large piece of concrete, and it's a perfect place to inflate a balloon. These balloons are about 150 feet in diameter when they're fully inflated, and they rise slowly if they're filled with helium in order to do that testing. Now we're going to look at some videos of actual rocket launches that have taken place at Spaceport America. This first one is taken from a camera which is on the rocket pointed back at the ground. And the first thing I want you to notice is that as the rocket takes off, it begins to spin. The reason for that I'm going to show you in a little while. But it's a good thing for it to spin when it's in the air, not a good thing once it's in space. And so there's a system on the rocket to slow that down, which you just saw there. You notice that the spin went from very fast to much slower. And again, in space, that's a much better situation to have. Now we're looking at another launch of the same rocket. Again, the camera is on the rocket pointing back at the ground. This time, however, the rocket has already left the ground when the video starts. So you'll notice it's spinning at a very high speed. Now again, it's a good thing for it to be spinning in the air, not in space. This rocket reaches a speed of about 5,320 feet per second. That's more than a mile per second. To put that in perspective, and by the way, there you just saw the D-spin. You saw the spin rate slow way down. This time it worked a little bit better. But again, let's go back to the speed for a moment. 5,320 feet per second, more than a mile per second. That means that if you can get to a place in 1 hour in a car, you can get there if you were able to ride this rocket in 1 minute. So much, much faster, very, very fast in fact. This rocket reached an altitude of over 77 miles above the Earth, and it got there in about 2 minutes. So again, very, very high speeds. Now once the rocket is in space, all the experiments that are on the rocket, these rockets only carry scientific experiments, and all those experiments are being performed automatically. They have equipment in place to make them happen and get the data that comes back to the ground. Now what you just saw happen there was the rocket motor that propelled the rocket to space, it can no longer be used, and so we just cut it loose and we're going to let it fall back to the ground by itself. But the experiments are all on the part of the rocket that you're still seeing there, and you can see it's still spinning a little bit. You can see the Earth there from very high above in the background. You can see the blackness of space. You can see the details on the Earth's surface. But all those experiments are being performed automatically, and then they're going to come back to ground by parachute. And to give you an idea of how fast it's going to land, if you were to stand on a desktop, say about 3 feet above the floor, and jump to the floor, the speed at which you would hit the ground or the floor is about how fast this rocket lands under the parachute. So it's slow enough that the experiments on board are not likely to be damaged. Now on the way up, that rocket had a powerful rocket motor pushing it, and it reached about 5 times the speed of sound. But on the way back down, even with only gravity pulling on it, it still reached a speed of about 3 times the speed of sound. As the rocket comes down then farther and farther and faster, the first thing that we do is we put out what we call a drogue parachute. That parachute is made of very strong fabric, and its job is to ensure that the large parachute, when it's deployed, isn't damaged by the high-speed movement through the air. And so there you can see the large parachute, and then eventually what's going to happen is you'll see them land on the ground, and they landed in a bush this particular time. This rocket landed about 30 miles away on White Sands Missile Range, and that's what was supposed to happen with it. And there you saw the landing, and that's the end of this particular video. And now we're going to watch yet one more launch of the same type of rocket. Again, this time we're going to watch it first from a camera on the ground, and we're going to watch the rocket take off, and you get an idea of how very fast it is when it takes off. Now we're going to go back and watch from the camera on the rocket pointing back at the ground, watch it start to spin, and then let's go watch it again from the ground. Now this particular rocket is going to seem to disappear here. This rocket burns a solid fuel very much like 4th of July fireworks, and once the fuel is burned up, it's very difficult to see. It's still there, but it can't be seen. Okay, now what's happened is the nose cone of the rocket has come off, and so what we're doing is we're looking from a camera back along the rocket. It's like we're looking at a pencil from the end. That's why it looks like a circle. The next thing we're going to see is the main experiment that was on this rocket, that round thing there in the middle, is pushed out because it needed to be out in space by itself. And this is the best part of all. If you'll watch carefully here, you're going to see the rocket and the rocket motor still attached without the nose cone, and then you're going to see a little flash, and it separates into 2 pieces. The part of the right comes down without a parachute. The part of the middle comes down with a parachute, and then the round object off in the distance also comes down with a parachute. And again, now it's coming down. We're looking along the rocket. First you saw the small drogue parachute, and then you saw the large main parachute that gently lowers it to the desert floor about 30 miles away. And now we have one more rocket launch that I'd like to show you. Now this time, instead of seeing all that smoke and fire, this rocket burns an entirely different type of fuel. In fact, the fuel that it burns is ordinary alcohol, the kind you might use to kill germs. So you saw it take off there, and you saw almost no smoke or fire because this type of fuel doesn't produce much. All right, now we're watching from the camera looking back at the ground again. And this particular rocket doesn't pull away nearly as fast, and this rocket isn't meant to spin. So when it does spin, that's not a good thing for this rocket, and there's a system on board to slow that down. Now the day when we did this launch, it was a little bit cloudy, so what we just saw there was the rocket going through the clouds, and mostly what we're seeing now is the clouds from above. That little bit of spin there you saw we didn't want to have happen, and so the system on the rocket slowed it down, so it's spinning, but very, very slowly. I have to apologize for the pink-colored streak along the lower right-hand corner. That was some oil that leaked on the camera lens, and we wish it weren't there, but unfortunately it is. Now again, we're looking back at the Earth from very high above, and you can see a lot of clouds, you can see the blackness of the space, and then finally the drogue parachute coming out. Again, we use two parachutes on both these types of rockets. The first one is the drogue, which slows it down enough so that when the big parachute comes out, it won't be damaged. And then it comes to the ground gently with the big parachute. The video of the rocket that you saw it spin. So does anybody know why we would spin a rocket?
So that it has enough altitude to get up?
Well, it's not really altitude. I'm going to show you why. So you ventured a guess, so we're going to start with you. So would you grab that by the handles? Okay, now what I want you to do is move it around, tilt it. Does it feel funny to you in any way? I don't think it does it? Okay, now let me spin it. Now try some of those motions. Now does it feel funny?
Yes.
Feels really weird, doesn't it? Would you say it feels like it's fighting back?
Yes.
When you try to turn it? Okay, that's why we spin the rocket. All right, now you want to try? So if you'll grab it, first get a feel for it. Now let me spin it for you.
That's cool.
It's cool, he said. Okay. All right, let's get Nathaniel. All right, so hold on to it, hold it out, get a feel for it. Okay, now let me spin it for you. Now try moving it. Now does it feel weird? It fights back, wouldn't you say? Okay, now your sister. Now try moving it again. Okay, now let's spin it. Okay, do you feel it? Okay,
Yes.
and now it's Kobe's turn. So hold on. All right, now let me spin it for you. Now does that feel weird? Feels like it fights back, wouldn't you say? So that's why we spin the rocket. So the rocket spins. So the rocket is, as long as it goes straight, everything's fine. But if it tries to go off course, that gyroscopic effect fights back. And that's why we spin the rocket. So there's another way I can show you that. I've got something here called a gyroscope. And this is a little gadget. It's got a heavy weight inside and it spins. So you see it there? So I can make that little weight inside spin. So if I set this thing down, let's do it right here. If I set it down there, what's going to happen? It's just going to fall over, right? But let's see what happens when I make it spin. So what I can do is I have an electric motor here, and I can make this spin really fast. It's like a top, that's right. So it's going to take it a few seconds to spin up, but I'm going to hold on to it until it gets spinning really fast. And you can hear it now, right? So it's spinning faster and faster. And once it gets up to a really high speed,
You don't want to put your fingers there.
okay, now that's about as fast as it's going to get. No, it's still getting faster. Okay, there I think we're about at the full speed. So I'm going to pull it off, and now let's see what happens. And see how it balances? So it's the same reason that wheel felt funny when you tried to twist it. So that gyroscopic effect is so strong that it won't even let that thing fall over. So again, that illustrates why we spin the rocket. It's like the gyro. Now what we're seeing here is it's going to start, this is something called precession. And it's much too complex to try to understand today, but it's going to tilt over farther and farther, and eventually it'll slow down because of friction, and it'll just fall over. Any questions? So let's go on and talk about something else then. When you make a rocket, or a car, or even a bicycle, we're just going to watch that for a while until it falls over. When you make something like that moves, do you usually want to make it heavy or do you want to make it light? Light, right. So what kind of things do we usually make cars and rockets and airplanes out of?
Metal and plastic.
Metal and plastic, okay. Any particular metal?
Aluminum.
Aluminum, all right. So aluminum is a good choice because it's not too expensive, it's pretty strong, and it's pretty lightweight. Okay, there's another metal that's even lighter that's called magnesium, and here's a piece of magnesium. So magnesium is even lighter, so if light is good, why don't we make rockets and airplanes out of magnesium? There are actually three reasons. One is it's quite a bit more expensive. Another one isn't nearly as strong as aluminum. And the third one I'm going to show you here in a few minutes. Okay, and then I have another piece of metal here, and this is really something. So I'm going to bring these around one by one, and I'm going to let you try each one of them. Okay, so that's a piece of aluminum. So what do you think of that?
That's heavy.
That's really heavy. So you know what that is? Does anybody know what that metal is?
What?
It's a metal called tungsten. And tungsten is the 6th densest metal that there is. Wow, isn't that heavy? Okay. Wow, isn't that amazing? Okay, Kobe, your turn. Okay, so we used to make the hot part of our light bulbs out of this metal, tungsten. It's the most heat resistant metal that there is, but it's also one of the heaviest. So it's a really good choice for parts of a rocket. If you need something that has to get really hot, then this is a good choice because it has the highest melting point of all metals. But if you need something that's light, this is not a good choice. So here's something really neat about tungsten. That piece of tungsten, it turns out tungsten and gold have the same density. Density is a property of materials that's for how heavy it is for its size. So gold and tungsten have almost exactly the same density. This piece of tungsten, if it were gold, this piece of tungsten is about $60 worth, okay? But if it were gold, does anybody have an idea how much it would cost? $3,000?
No, 3,000K.
$3,000K, $300,000? That's a little high. It's actually about $60,000. I looked it up just a couple days ago, and if that were a piece of pure gold, that size, it would be $60,000. It was $60,800 actually. And so that means that if you were to take that piece of gold to any car dealer in Las Cruces, you could probably drive away with one of the nicest vehicles they have on the lot for that amount of money. Okay? So now I told you that magnesium is even lighter. And I mentioned that there are three reasons why we don't use a lot of magnesium in making rockets and airplanes. It's not as strong, it costs more, but here's the third one. And I hope we can get this to work out here in the with the wind, but I think we can. The wind seems to have died down a little.
Lead?
It's a metal called magnesium. And so you saw what happened there, right? It actually burns. So you can imagine if you made an airplane out of magnesium and you had a crash, thin pieces of it burn. So it's the same as this metal right here. In big pieces, it doesn't burn very well, but in thin strips, like you might make the skin of an airplane, it burns really well. So that's one of the reasons we don't use it. Okay, any questions? So how many of you have ever used your mouth to suck the air out of a soda bottle? Okay, the bottle kind of collapses, right? Okay, so I've got here something called a vacuum pump. Whoops, it's hooked up. I have this thing called a vacuum pump. And this vacuum pump does the same thing you can do with your mouth, only it does it a lot better. So if I hook up, so when I turn this thing on, it makes a little noise. Okay, but when I turn it on, I'm going to hook up this water bottle to it. All right, now I'm going to turn the pump on, and it's going to make a little noise. Right now I'm not pulling a vacuum on it because I've got a valve here that I have to open. So when I open the valve, let's see what happens. So you'd say that's a pretty flat bottle, wouldn't you? Okay, so again, it's the same thing you could do with your mouth, except this vacuum pump does it a lot better. Now the vacuum pump, I can do some other really neat experiments with it, because when we go to space, space has several really interesting properties, but one of them is it's a vacuum. So I can actually use this vacuum pump. I'm going to stop this and get out of the way. I can use this vacuum pump to make sort of like artificial space inside this jar. So I've got this thing called a bell jar, and it's shaped like a bell, even sounds like a bell, right? Okay, so I can put it on this plate, and I can hook the pump up to it, and I can then use it to pull the air out. And then once I've done that, I've made artificial space inside here, at least as far as the vacuum property is concerned. But if I do that, how can I prove to you I've done something? vacuum is invisible, but so is air. So if I take the air out, how can I prove to you I've done something? Well, I'm going to prove it to you by putting a balloon inside. All right, so just a little water balloon, and I'm going to tie it off, and I'm going to put it inside the bell jar. I usually put a static charge on it so it sticks to the top, makes it a little easier to see. Okay, so now if I turn on the vacuum pump, I start pulling the air out. Let's see what happens. Okay, so I'm going to close that valve. Okay, so the pump is on, and as soon as I open this valve, I'm going to start taking the air out. So let's watch. Open the valve, and we'll see it starts to get bigger. Okay, so now I'm going to stop that. So why would the balloon get bigger? Well, what determines the size of the balloon? The balloon has air inside pushing out, right? But it has air around it that pushes back. So the size of the balloon is determined by the balance between the air that's inside pushing out and the air around it pushing back. So if I get rid of some of the air around it, then the balloon can get bigger because it isn't pushing back as hard. Okay, so if I were to let the air back in, what should happen then? It should get smaller, shouldn't it? Okay, so remember, science is always about doing the experiment. We always want to do the experiment to prove our ideas. So let's let the air back in, and look at that. It got smaller just like we expected. So now the question would be, can I make it pop? So let's go ahead and see if we can get it to pop. So again, we're taking away the air around it, and notice it's not very loud when it pops. The reason it's not very loud is because when you study sound, some of you may have already studied sound, when you study sound, you learn that sound requires air to get from the source of the sound to our ears. Well, I got rid of most of the air in there, and so there's not much air to transmit the sound. Now, you saw how the air pressure crushed the balloon, crushed the bottle. Let's look at this. So this heavy aluminum plate, I can pick it up really easily because the air pressure that crushed that bottle is also holding the bell jar onto the base plate. So that's why I can do that so easily. Okay, so now let's stop this and let the air back in. Okay, so I can let the air back in. I'm going to turn the pump off briefly so I can make it a little quieter. Okay, so that, now you'll notice it comes right off. Okay, so now, next question for you. If you were to tell me one thing about boiling water, what would you tell me?
It's hot?
It's hot, yeah. What if I told you I can boil water without making it hot?
You just make it cold.
Okay, so I'm going to tell you I can make water boil without making it hot. Okay? So let's get rid of some of this residue of the balloon. And now what I'm going to do is I've got here a bottle, and it's got a little stone in it. The stone, all that does is make this work just a little bit easier. So I've got a bottle of water here, just ordinary bottled water, and I'm going to dump some of it in here. That should be about enough. And let's put that on there. I'm going to put the bell jar on around it, and let's see what happens. I can't guarantee this will work because it doesn't always, but usually it does. Okay, so I'm going to start the pump, and now I'm going to open the valve, and now we've already started to pull the vacuum because you can see it's stuck there. So we're going to keep pumping here for a while, and we should see the water start to boil. Now I'm going to be able to know that's about to happen because the vacuum pump is making a sound, and as the vacuum pump gets ready, as the water gets ready to boil, the pump is going to start to make a different kind of sound. So I usually can tell when it's about to happen. All right, so notice the sound that the pump is making. It's quieted down a little bit, and now it starts to make kind of a rattly sound part of the time. And once, yeah, so it's not started yet, but hopefully it will soon. Okay, yeah, now you see a few bubbles in there. What we're seeing there, those bubbles are actually dissolved air coming out of the water. Okay, so sometimes this takes 5 minutes. Hopefully it won't take that long today. All right, keep watching. It's starting, I think. It's getting pretty close because the pump is starting to make the other sound more of the time. As soon as the pump starts to make that other sound all the time, it usually starts to boil. All right, and there it goes. Now, does it look like it's boiling?
Yes.
And it is boiling. But you know what? It's not hot. And I'm going to prove that to you because I'm going to stop the pump. I'm going to let the air back in. And now I'm going to just put the lid on so we don't spill it, but I'm going to pass it around and you can feel for yourself that water's not hot, right? Okay, so we made the water boil without making it hot. Okay, now we've seen two things that happen in a vacuum. We've seen how the balloon broke. Well, think about our bodies. Our bodies are a little bit like balloons, right? We've got air in our lungs. How many of you have ever driven over a mountain road and felt your ears needing to pop? That's because there's air trapped inside our ears, and until that pressure equalizes, it can be painful. Okay, so our bodies are a little bit like balloons, but you know what? Our bodies are also about 70% water. Well, you saw what happened to water there, right? So let's imagine what would happen to an astronaut in space if they weren't in their spaceship or in their spacesuit. Their body is like a balloon, so it would tend to expand, and a lot of the water in their bodies would want to come out. So let's do a little experiment here. Let's use a stand-in for an astronaut. So we're going to use a giant marshmallow, and we're going to pretend that this is an astronaut. So I'm going to take one of these marshmallows, and I'm going to seal this back up so that they don't dry out. Okay, so I'm going to put one of the marshmallows inside. Now this is going to be something that you'll need to see from fairly close. Let's see, I need to dry this off just a little bit because I've got some water vapor that condensed inside, and if I don't get rid of it, it's going to make it a little harder to see. All right, so here we go. So I'm going to put that on the base plate, and I'm going to turn on the pump, and I'm going to open the valve then. So as soon as I open the valve, I'm going to start pulling the air out. All right, so are we ready? Let's see what would happen if that were an astronaut. So would you want to be an astronaut in space without your spacesuit? No, you wouldn't, would you? So let's keep after this for a little bit. See, it got a whole lot bigger. And so what's happening there? Well, you saw what happened to the balloon, right? The balloon expanded, and now it's shrinking. Okay, so the balloon expanded and then it popped. Well, what is a marshmallow? It's a bunch of bubbles of air that are trapped inside sugar, right? So just like the balloon expanded, those little bubbles expand. But you know what? The balloon popped, and so some of those bubbles are popping right now. And now, if we keep doing this for a while, usually we're going to see it start to expand again because a marshmallow also has a lot of water in it. Have you ever had a stale marshmallow? You know, they're not much fun to eat, right? They get really hard. Okay, so that's because they've lost some of their water. So we're also pulling some of the water out of that marshmallow right now. And so usually what we'll see is it starts to expand just a little bit again. I'm not sure this one's going to do it too much. Okay, but now when we let the air back in, we're going to see what would have happened. Okay, so I'm going to stop the pump. I'm going to let the air back in. And you can see that that marshmallow isn't quite what it started out to be. Now, it's still edible. I mean, it's still the same marshmallow, it just doesn't have the air in it, except we wouldn't want to eat it because my grubby hands have been all over it. And now once we pass it around to everybody, you can pass it on to the others. Once everybody's touched it, then it's got germs from everybody on it, so we wouldn't want to eat it. Okay, any questions? Okay. All right, so I want to do one more experiment for you. Actually, it's going to be kind of a double experiment. And so we launch two types of rockets here at Spaceport America. We launch rockets that use solid fuel, and we launch rockets that use liquid fuel. Now, solid fuel rockets, the fuel that they use is a lot like 4th of July fireworks fuel. So they make a lot of smoke, and they leave a trail of smoke as they fly until the rocket motor burns out. Once it's used up all of its fuel, then it still coasts on its way to space. The other type of rocket that we use uses a liquid fuel. And the one rocket that we launch a lot uses ordinary alcohol as its fuel. So the same stuff that we're all using every day to kill the germs on our hands, that same alcohol can be used as rocket fuel. And you know what? I've got some of it in this little bottle. So this little bottle makes a little spray. You should be able to, can you see the little cloud of mist? Okay, so what I can do is take that alcohol and turn it into a vapor. So what I'm going to do is I'm going to put some of it in this bottle. And in order to make this work, what I need is a source of ignition. So I'm going to use this. Does anybody know what that is?
Well, it actually used to be a lighter. It's not a lighter anymore because it used up its fuel a long time ago. But you know what? It still makes a spark. And we're out here in the bright sunlight and you probably can't see the spark. But if we were inside, we'd be able to see the spark. It's just a little blue spark, just a tiny spark. So what I'm going to do is I'm going to take a cork and I'm going to put it in that bottle lightly. And I'm going to put 3 squirts of alcohol in. All right? Then what we're going to do is we're going to count down from 3. So if you'll help me count down, 3, 2, 1. Okay, so that's what happened. We set off the rocket fuel inside. So now, at this point, somebody usually asks a question. How would we make this work better? Any ideas?
You put solid fuel in there?
Well, what with just the alcohol? Somebody usually asks, put more in, put 4 squirts in, or put 5 squirts in. What do you think of that idea? Okay, well, you know what? It wouldn't work as well. And here's the reason. What we try to do, we try to put just the right amount of alcohol inside for the amount of air that's in there. So if we put more alcohol inside, there won't be enough air for it to burn up. And so we will actually force some of the air out and it won't work as well. Likewise, if we only put 2 squirts in, there won't be enough alcohol for the amount of air that's in there and it won't work as well either. So I've done this so many times that I know that 3 squirts is the right amount. And so that's when we get the best effect. All right, now I'm going to show you one more experiment with this. So here is the super duper version of the same thing. Okay, so what I've got here is this is a gas grill lighter and it makes a little tiny spark. Again, I don't think we can see it out here in the bright sunlight, but it makes a little spark. And I'm going to put 3 squirts of alcohol inside a bottle and we'll see what happens here. Now before I do this, earplugs, because you'll hear why here shortly. All right, so I'm going to do this away from you guys so that it's not going to be too loud for your ears. All right, so I'm going to put in 3 squirts. 1, 2, 3. All right, then I'm going to put it over this. And I'm going to walk over here to the side so that everybody is far enough away that they don't hear the loud sound. All right, so let's count down from 5. 5, 4, 3, 2, 1. It did, didn't it?
Sounds like a gun.
Okay, so everybody likes that experiment. And the thing is, we're lucky here we can do it outdoors because we can't do this inside. We usually do these experiments inside in a classroom and it's just too loud to do inside. So we usually like to do it outdoors. Okay, so what I want to do is encourage you all to study your math and science because some of these neat things that we have to do here at Spaceport America, we have to know a lot of math and science. Every job here at Spaceport America requires that you use math and science. So my job, I have to help launch rockets, and obviously I have to know a lot of math and science to do that. But every job here at Spaceport America requires that. If you're a firefighter, you have to know how to put out fires involving exotic rocket fuels. And so you have to know a lot of chemistry in order to do that. If you're a security guard, you have to know what to do if there were a fire or something and the smoke was blowing in a certain direction to keep people out of it. Every job here, the high-tech systems to operate this building, it's a very complex building. We have to program the system. So everybody that works here has to know a lot of math and science. So if you want to work at a place like this, go out there and study and learn it now because it's going to be easier to learn now than any other time. Any questions?
Wow. That was cool.
Okay. All right. I think that's about it. My name is Dr. Bill Gutman. I'm the Director of Aerospace Operations here at Spaceport America. We're standing at the entrance to the spaceport and we're standing in front of a replica of the Virgin Galactic spaceship. This is the spaceship that they take people to space in. And so my job here at the spaceport is to deal with those kinds of things, to make sure that those are safe. But you know, the STEM careers are very exciting and we'd like to encourage you all to study your math and science because if you want a job like mine, you're going to need to know a lot of it. But you know what? That's not the only type of job we have here at Spaceport America. We have firefighters, we have security guards, we have people that maintain the buildings, and every one of those positions requires that people know a lot of math and science. The firefighters, for example, have to know what
how to fight a fire. If there should be an accident involving one of the spaceships, they use special fuels, and sometimes the best way to put out that fire isn't to use water but to use some chemical. So they have to understand a lot of chemistry in order to be able to do that effectively. Our security guards have to know if the wind is blowing. Let's suppose something happens and there's some smoke from a fire that could be hazardous. They have to know how to predict where that smoke is going to go. So every job here at Spaceport America requires math and science, and so I encourage you to study that hard, because if you want these kinds of jobs, if you want to work at an exciting place like this where you get to work with spaceships, then you need to have that kind of background.
I'm Mike Orman. I'm part of the security team, safety team here at Spaceport America. To the right of me here is where one of our main entrance stations are, and people that access the facility have to come through here, and we verify their authorization to be on site. We've part of the most important greeting part of Spaceport America is greeting the customer and making sure that they are again authorized to be on the facility. Been in law enforcement for a lot of years prior to doing this, and saw this as a wonderful opportunity to continue in a spaceport where I knew that I would never be a astronaut or a rocket scientist, but it would still allow me the opportunity to work in an extremely exciting area and see some history being made right here at Spaceport.
Hello, my name is Lieutenant Davis at Spaceport America Fire Department. I'm one of 6 firefighters here that work a 48-96 shift. That means we're on for 48 hours straight and we get 96 hours off, which is pretty nice. We're out in the middle of nowhere, so we have to be well versed in a little bit of everything, anywhere from our structural and EMS, but also wildland firefighting, rope technical rescue, hazardous material, and of course aircraft structural firefighting. So a little bit to be involved out here as far as qualifications, but it's phenomenal to work here. It's not just to be rocket scientists out here, but you also can be a firefighter, EMTs, and be able to see all kinds of neat and innovative things. So it's a great place for research and development. I'm glad to be a part of this facility.
So I'd like to thank you all for joining us today for our tour and our experiments. Again, we're going to close out our day with standing here in front of the gateway to space. Again, this is the building that we are using to carry people to space. This is the base of operation for doing that. Again, thank you all for participating today, and we look forward to seeing you again in future videos.